In this video, we're going to be continuing looking at some trigonometric identities, specifically the three Pythagorean identities and then also the sum and difference. So this slide has the basic identities, most of which you guys learned in your previous trig classes. The reciprocal identities are taking an existing trig function like the sine of an angle and taking the reciprocal, taking that fraction and flipping it over for cosecant. Secant and cosine are reciprocals, and tangent and cotangent are reciprocals. We also have the cotangent identities, which are that tangent is equal to the sine over the cosine. That comes from this idea that if we're on the unit circle and we have some point in particular, let's call the coordinates of it x, y. This triangle here, and the angle would be sitting here next to the origin. Again, when we're on the unit circle, the radius here is equal to 1. And so the cosine in this particular case will end up being x over 1, or just x. And the sine of the angle will be y over 1, or just y. And so taking that idea of opposite over adjacent, we'll get y over x for the tangent, or sine over cosine. And then we also have these even and odd identities. They have to do with what the graphs of these functions look like. Again, an odd function is one like sine, in which when you, let's draw just a rough sine graph here, if you take a particular function or a particular angle, let's say pi over 4 versus negative pi over 4, the output values are going to be opposites of one another, have negative values from one another, versus the cosine, where the graph is symmetric about the y-axis. If I were to look at, say, pi over 4 versus negative pi over 4, the output values are going to be the same. The only identities that are even or the only functions that are even are cosine and therefore secant, and the other four are all odd. Identities, they are extensions of the Pythagorean theorem. The Pythagorean theorem, the way that we typically learn it in a geometry class, is a squared plus b squared is equal to c squared. And if we are, again, looking at a particular point on the unit circle, let's say, I'm just going to make it easy, I'll just look at something in the first quadrant. Let's say that the coordinates here are x, y, and then this length here is 1 because it's a unit circle. This length is x and this length is y. We get this equation here, x squared plus y squared is equal to 1, or 1 squared. And then relating x and y to sine and cosine, we get this different version, cosine squared plus sine squared equals x. Most commonly, we write it with the sine of the angle first. And I think I mentioned it before, but just in case I haven't, this notation where we put the square symbol right next to the function, they're using s as the arc length, but we could have, it could be an angle or something. This is the same as sine of s squared, or sine of s times sine of s, right? It's just a notation that we use where the square isn't sitting outside the whole thing, it's sitting next to the function. We want to make the distinction that the angle, or the arc length in this case, s, is not what's being squared. There are different forms of the Pythagorean identity, and they come pretty easily from the first one. If we start with the original Pythagorean identity, and we divide every single term by sine squared, as long as you do the same thing to both sides of an equation, you're still keeping everything balanced. Sine squared over sine squared is just 1. Cosine over sine is cotangent, but these are squared, so this will be cotangent squared. And then 1 over the sine is the cosecant. So dividing everything by sine squared, I get the second identity. And then similarly, I can do the same thing, but instead divide everything by cosine squared. And sine over cosine is tangent, so we'll have tangent squared x. Cosine over cosine is going to be 1, and then we'll have secant squared. So again, you can derive the other two Pythagorean theorems pretty easily from the first one, just dividing by either the sine squared for everything or dividing everything by cosine squared. The equivalent forms that we see here are just subtracting one of the terms onto the opposite side of the equation, and we use that sometimes for substitution purposes. Often with trig functions, we're trying to eliminate one particular function and get everything in terms of one function, and so these are equivalencies that we'll use. So here is an example problem. We want to factor this and simplify it as much as we can. I can see that both terms have a cosine squared in common, so I'll factor that out to the front. And I'm left with sine squared of x plus cosine squared of x. This is a Pythagorean identity, right? This is the first Pythagorean identity. This is just equal to 1. So I'm ending up with just the cosine squared of x. That was pretty easy. Here are two different examples where we have multiple trig functions and we want to simplify them as much as we can. This first one, letter A, is looking at those even and odd identities that we were talking about. But one general strategy that we use when we have trig functions is to write everything in terms of sine and cosine as a first step and then see if you can simplify. So I'll do that first. Cotangent is the same as cosine over sine. And then cosecant is 1 over the sine. Okay, this is called a complex fraction. I have a fraction and with two fractions within a fraction. So I'm going to multiply everything by sine of negative theta over sine of negative theta. By doing that, this is going to cancel and this is going to cancel. And it looks like I'm left with just, in the numerator there, cosine of negative theta. And because cosine is an even function, plugging in the negative angle will give us back the same value as if we plugged in the positive angle. So our final answer is going to be just cosine theta. It's a much simpler form than what we started with. Looking at letter B, what I have in the numerator looks like something that I might want to try to factor. And then in the denominator, I've got two different trig functions, and so I want to try to rewrite that in terms of one trig function. Since the majority of what I'm seeing is sine, I probably want to try to change that cosine squared also into sine squared. So let's look at the numerator first. I'm going to do a little variable change. Let's let x be the sine of t. I'm just looking at the numerator first. So instead I'm going to write this as 2x squared plus x minus 3. So that makes it easier for me to think about the factorization of this. So I've got, I think I'm going to put a 3 here. This will be a plus, and then minus 1. Let's see if that works. It'll give me a plus 3 and a minus. Yeah, that's going to work. So that's the factorization of that. Changing it back to the original problem, I'll write it as 2 sine of t plus 3, and then sine of t minus 1. I'm just substituting sine of t instead of the variable x. In the denominator, I see that this is one of the equivalent forms of the Pythagorean identity. If I subtract cosine from both sides, I have 1 minus cosine squared t. So I'll substitute that instead for the denominator. So in the denominator, I'm going to have sine squared t minus sine of t. And then I can factor the denominator. So I'll leave the numerator as it is. And then in the denominator, I'll factor a sine of t out to the front. And I have sine of t minus 1. That works out kind of nicely because I get these two factors canceling. And then this gives me 2 sine of t plus 3 over sine of t. Or 2, I'm going to divide sine t into both terms, plus 3 over sine of t. I think I'm going to write this as 2 plus 3 times the cosecant of t, just taking that reciprocal of sine. 1 over sine changes into cosecant. That's a much simpler format than the original that we started with. And in calculus, when we get into some of our integration techniques, we really want to simplify our trig functions to make them easier for us to manage. All right, one more example here where we are trying to add some things together, and we've got the first term being a fraction. And so we need to get a common denominator to start off. So I'm going to start by multiplying this first term by 1 plus sine of x over 1 plus sine of x. I'm doing that so that both terms have the same denominator and I can combine them together. So cosine of x plus tangent of x times 1 plus sine of x over, they both have the same denominator now, so I can combine them. So cosine x plus tangent x. What I'm doing right now is I'm going to distribute this tangent of x to both of these terms. And let's see, if I take, I'm going to do work on the side here, if I have sine multiplied by tangent, which is, tangent is sine over cosine. And I'm multiplying that by the sine. That's going to be sine squared x over cosine of x. And then on the bottom I've got 1 plus sine of x. I think since I'm writing everything in terms of sine and cosine, I think for this tangent here, I'm also just going to write that as sine x over cosine x. Okay, because I've got now again a complex fraction, and so to clear all the denominators, I multiply by whatever that denominator is. Common denominator is going to be cosine x. I'll multiply both top and bottom by cosine of x. Let's go over here to the side. I'm going to move up here. So I'm going to first multiply over here. That's going to give me cosine squared. Then I'll multiply here. The cosines are going to cancel. And then I'll multiply here. The cosines are also going to cancel. And in the denominator, I'm not going to multiply it. I'm just going to leave it like that for a second. Cosine of x multiplied by 1 plus sine of x. Okay. And that's because in looking at the numerator, I see I've got a Pythagorean identity sort of hiding there, right? I've got cosine squared plus sine squared. Those two together are going to equal 1. So I've just got sine of x plus 1 over cosine of x multiplied by 1 plus sine of x. And then these two terms will cancel. So we have 1 over cosine of x, which is equal to the secant. That's a much simpler format than what we started with, right? All right, this is a technique that we use for trig substitutions. It sometimes involves things with drawing a triangle so we can get different trig functions that we can use. So this looks a little funky at first, but just bear with me, it'll make sense in the end. When we end up with something with a square root like this, where we've got 9 and we've got x squared, we use a trig substitution to simplify this. And when you get into calculus, you'll learn what the appropriate trig substitutions are. So in this case, we're going to use x, we're going to make x equal to 3 times tangent theta. There are rules that we use to determine what they're going to be. We'll talk about that later. So let's start by looking at the expression that we're given. We have 9 plus x squared, square root of the whole thing. And instead of x, I'm going to put in its place 3 tangent theta, and that's going to be squared. I'm putting that instead of x. So I've got 9 plus 9 tangent squared theta. I just squared both of those items. So then if I factor a 9 out, and this is the reason that we use this substitution, is that we end up creating a Pythagorean identity. This is the same as secant squared theta, which is nice because now underneath the radical symbol, I have 2 perfect squares so that I can take the square root of this whole thing. The purpose of this trig substitution is so that we can get rid of the square root. And I end up with 3 secant theta. Everything's positive. We can assume everything's positive because we're in the first quadrant here, right? Between 0 and pi over 2. All right. Now, let's draw a triangle because they asked us to find both the sine and the cosine. And we know right now that 9 plus x squared is equal to 3 secant theta. And we also know that x is equal to 3 tangent theta. That was our original. So if I divide both sides by 3, I have x over 3 is equal to tangent theta. We're going to use this information to draw a triangle. Again, we're in the first quadrant, so I'll draw the triangle like this. Theta is here. Tangent is opposite side over the adjacent side. So I'm using that for labeling. The opposite side, x, is going to go over here. The adjacent side, 3, is going to go over here. And if I rearrange this guy, I have 9 plus x squared over 3 equals the secant of the angle, which is the hypotenuse over the adjacent side. We could have used the Pythagorean identity as well, but that's really how we got this. This is what the relationship has to do with the Pythagorean identity. So this hypotenuse here is going to be the 9 plus x squared, right? And that works out, right? Because if I squared these two sides, I'd have x squared, 3 squared would be 9. So that makes sense. All right, so now we can use those to figure out the cosine and the sine. The cosine of the angle is going to be the adjacent side over the hypotenuse. And the sine is going to be the opposite side over the hypotenuse. We could leave it that way. Technically, we should rationalize everything. Get that square root out of the bottom. And so an alternate version would be 3 times square root 9 plus x squared over 9 plus x squared. And then for the sine, it would be x times the square root of 9 plus x squared over 9 plus x squared. So these are just alternate versions, taking the rationalization into effect. The last slide has sum and difference identities. When you're trying to find an exact value for a value that's not on the unit circle, you use these different identities. And there's an example here that's using one of those formulas to figure out the cosine of 5 pi over 3. And what you have to do is first find two angles that are known angles from the unit circle so that you can use the values. The formula for cosine, in this case, of A minus B is cosine A cosine B plus sine A sine B. And so what they've done is they've taken the values for each of those cosine sines, plugged them in, and then simplified. I'm not going to spend too much time going over the sum and difference formulas, only because there are calculators online you can access that will give you the exact value. Just be sure that you find a calculator that gives you the exact value rather than a decimal, and we can talk about in class a couple of different options that you have, because there are some that will end up with a nested square root, and those are not as useful. They're a little bit more complicated to simplify. So again, we'll talk about that more in class. All right, have a great evening. I'll see you later.